Okay. Yeah, so it's my great pleasure to introduce Professor Boris Hanin from Operations Research and Financial Engineering. So for those of you who don't know, I'll just read a bit of a bio for Boris. So Boris has been an assistant professor at Princeton Orphy since fall of 2020. His research interests are on machine learning, probability, and mathematical physics. Prior to Princeton, he was an assistant professor in mathematics at Texas A&M, and he's also held visiting positions at Google, Facebook AI, and the Simons Institute. And so today, Boris is going to talk to us about optimization and generalization in overparameterized models. And before we begin, I just want to remind everyone that this talk is being recorded. So Boris, take it away.
Thanks, Jason. Yeah, hi everyone. I don't know everyone on this call. Hope you guys are doing well. It's nice to meet you, those that I haven't met before. So I wanted to try to give a somewhat unusual talk. So this talk will not be about my work. It'll be about kind of a set of questions that I think are really fascinating. And my goal isn't going to be to try to formulate and prove the latest and greatest theorems, but rather tell you what the questions are and why I think they're kind of interesting and why they require some new ideas, and to just give sort of as much intuition as I can on the subject. I'm sort of learning it myself, you might say. So in particular, I think that in the last maybe 5 to 10 years, the idea that overparameterized models are good, both for optimization and for generalization, has become very popular. And, I'm neither a statistician nor an optimization person by training. So, I'm probably going to be saying many things in a suboptimal way, and many things that I say, I'm probably missing some key points. So I really encourage this to kind of be interactive, interrupt me, tell me what you think and what I'm doing wrong, because that'll make it useful for me and I hope for everybody else. Okay, so here's the setup. Let me introduce a little bit of notation. It's very basic, but still. So we're going to consider a model, and I'll think of it as some parameterized model y is f of x comma w. Okay, so w are some parameters. It could be the weights and biases of a neural network. It could be pretty much anything you want. And our goal is going to be to fit the parameters y to some data, fit in some way to data. So for me, data is just a data set, and I'll write it as script D. And I'm going to have xi comma yi as the kind of input-output pairs. And I'm going to write n sub d for the number of data points. Okay, and the kind of optimization procedure, the fitting procedure I have in mind is empirical risk minimization. Okay, so by minimizing an empirical risk. Okay, I'm going to try to keep it high level, but I need to at least introduce the risk. So this is my training loss on a collection of parameters w. This is the average over the data set of the per sample loss. So I have some loss function little l, and it tries to compare the current output of my model with the correct output yi. Okay, so this is somehow the paradigm in which I want to work. And maybe just for a word of context, I mainly think about neural networks when it comes to machine learning these days. So certainly this is how neural networks are trained, at least on supervised learning tasks. Okay, and the kind of definition, and I'll put this in quotes because I don't think it's a real definition, but it's somehow meant to be an intuitive one. So this model F is overparameterized. That's the thing in the title. If the number of parameters n sub p, so this is the number of parameters, it's the dimension of the space in which the vector w lives, is greater than the number of data points. Okay, so in practice, at least again in the neural network world, it is extremely common for models to be vastly overparameterized. You have way more free parameters than data points you're trying to fit. Okay, and then I'll introduce one more piece of notation. So I'll call it L subtest of W. So this is like how well you're doing on a new piece of data. So this is just the average over a new draw of an XY pair of the loss, at the current model that you have. Okay, so I don't know everyone's background, so I'm just trying to be more or less complete in introducing the notation. And I call this the test loss. I think people sometimes call it the risk or I don't know. People have different names and I don't know all the names. Okay, fine. So that's the setup. That's the notation. Hopefully I won't have too much more notation. And I now want to set up the basic tension of the talk, why I care to study some kind of questions about overparameterized models. So I'm going to remind you, and I sort of apologize in advance because, you, I'm sure, know it way better than I do. So this is the classical bias variance picture, bias variance trade-off. Something that we believed for a long time, but I'm going to tell you, is not really necessarily true. So how are you supposed to draw it? Well, you draw on the x-axis some notion of model complexity. So here I'll draw the number of parameters. And on the y-axis, you're supposed to plot the model performance. So this is some measure of error. And then what's supposed to happen? Well, okay, so there's two kinds of error you can draw, right? There's the training error. So this is L train. This is what your training error does after you've optimized your model. And of course, this here is the interpolation threshold. Maybe I'll actually use a different color. I don't think red comes out very well. So this is roughly when the number of parameters is equal to the number of data points. You are able to fit all the data and the training error goes to 0. But then of course, you don't actually care about the training error. In the real world, we care about the test error. And so the test error first goes down and then it starts to go up and it often diverges at the interpolation threshold. Right, and so somehow the classical picture is supposed to be that this is the kind of bias variance optimum. And again, I'm assuming you guys know this better than I do, but still somehow the idea is that if your model is too complex, if you have too many parameters, then sure you'll fit the data, but you'll also fit the noise in the data, and so you won't do well on unseen data. And there's some trade-off between the complexity of your model and its ability to fit the actual patterns in your data, and then the complexity of the model overfitting to the data. And those are the words people usually use. So here the model is underfitting. Right here the model is overfitting. And here you're overparameterized when you're to the right of this interpolation threshold. Okay, so that's at least the picture that I saw when I was growing up, so to speak. But this picture just, it turns out, is misleading. And that's what I want to kind of focus on. So however, in modern ML tasks, e.g. in neural networks, that's sort of what I know, but this is a rather robust thing. We often have that the number of parameters is much bigger than the number of data points. The model fits the data perfectly, fits the data. So L train, is identically 0. And the model generalizes. Model generalizes, i.e. the test loss is small. And so the question I want to try to ask is that how is this possible? Certainly, this kind of very general formulation of the question has driven a lot of theory for neural networks. And I think it's certainly not fully resolved yet. And, I just want to point out that there are two mysteries here, more or less. Mystery number one is that typically this loss that you're minimizing is rather non-convex as a function of the weights and biases of your network or whatever your parameters are. And yet we're actually able to drive the training loss to 0 by some relatively simple-minded optimization scheme like gradient descent. So the fact that we actually get the training loss to go to 0 is one mystery. But then the second mystery, which in some sense is more profound, is that your test loss is small. You actually do well on unseen data. You're not just memorizing the data points. Okay,
Boris,
so,
can I ask you?
Yeah.
Boris, can I ask a question? This is Mete. In the test error that you defined, you're taking an expected value. So in practice, I would not know this distribution of x, y. So this is, how should I think about the expected value x, y? Because, okay, if I'm doing an academic experiment that I may just simulate things and I would know that, but in general, I probably don't know that distribution.
Yeah,
right?
so the standard practice is you take your data set you start with and you actually split it into two parts, one on which you train and the other on which you validate. So you never see the training points in the validation set, and you simply approximate this by the empirical average over your validation set. So this is the sum on, let's say again, you have this many, and I'll call them f of xi tilde. So, that's an unbiased estimator roughly for this.
Okay, so it is important that the n sub d is large so that this second approximation is good enough.
Well, I mean, so it depends what you mean by important. Of course, in practice, it's important. In some sense, I'm happy to just write down this expectation. And, if I can prove a theorem that the expectation is small by whatever method I have, then I'm pretty happy. Like in statistical learning theory, things are agnostic to the data distribution, in fact. So you don't have access to it, but you can still sometimes prove things by various techniques. But that's kind of the standard method. Yeah, other questions? Okay, so I want to present two very influential empirical papers. I won't present them in full detail, of course, but I want to say something about them. So, in this neural network world, if you just say Zhang et al., people know what you mean. That's how famous this paper is. So here's, I want to describe the experiment whose results they've plotted here on the left. Okay, so what we're looking at is there is a single model. So there's a single neural network trained to fit what's called CFAR10. So CFAR10 is a standard kind of computer vision data set. The inputs are images, and there's one of 10 possible classes for each image. It's a classification task. It's like car and frog and airplane. I don't remember all the classes. Okay, and the way to read this experiment is you take the true data set CFAR10 and you fix your model. And every time you train it, by gradient descent from a random starting point. And so let's look at the blue curve first. So this blue curve is the true labels, and that means you haven't corrupted the data set at all. You just take the true data set, and what you see, the fact that this blue curve goes to 0, so the x-axis here is the time during training. It's the number of steps of gradient descent you took. And the y-axis is your test loss, your training loss. This is just the loss on the data set. You're not actually generalizing yet. So this is just saying that you're fitting the true data. Okay, so the first thing we learn is that the neural network we have fits all the true data points. That's the blue curve. Okay, and that's not surprising in some sense. That's like very standard in the neural network world that you can memorize your data. But here comes the kind of interesting stuff. So all these other curves are, you take that same data set and you do something rather bizarre to it. So for example, this green curve here, what do you do? So each image is, some n by n array of pixel values, and you take a fixed permutation of that array and you apply that same random permutation to every single image. So you took things that used to look like airplanes and you scramble the pixels around, and it really doesn't look like an airplane anymore at all. And you still label it by whatever the correct label is, and you train on that. Okay, so that's one kind of corruption. Here's another kind of really interesting corruption. Let's say this pink line. So here you just replace every single pixel by IID random Gaussian noise. Okay, so you have complete nonsense for the input, and you still have the 10 possible labels, and so on. So each one of these curves is a different curve, different corruption for your data set. And what you learn is the following. So the second thing to note is that your particular neural network fits complete noise. For example, if you just have completely random pixels, then, okay, of course, there's no structure in your data set at all. You're just memorizing completely noisy input, and you're associating it to one of the 10 classes. So somehow the neural network both fits true data, perfectly interpolates, and fits completely noisy data. Okay, but the third thing to note, and this is the thing we're about to see on this kind of plot on the right, but let me write it down first, is that the neural network still generalizes well when trained on true data. Okay, i.e. the test loss is very good. So on this column on the left, there's this different neural networks that they did this experiment for. So for example, this top network is some network that when they were doing these experiments was close to state of the art on these computer vision tasks. It has a relatively large number of parameters. NP is about 1.7 million. And you see that basically no matter what they did, the training accuracy was 100%. They perfectly fit the data. You know, this training accuracy down here is when the data was completely random, when the labels were random. And what you see is that, you know, in these top four things, the test accuracy, when you actually ask how well the model did on a new example, is really very good. 85, 90% is quite good, or at least was good back then for CFAR 10. And of course, you know, you get complete random chance on the version of the data set when you're just memorizing pure noise. You can only have 10% chance of getting it right because there are 10 possible classes, so everything is just a random guess. Okay, so somehow the neural network completely fits noise and yet generalizes when trained on real data. Okay, and what I want to say is that there's kind of a big implication to this, which is very interesting and goes against the usual kind of philosophy of statistical learning theory, at least in the most orthodox sense. So this tells you that any theory of generalization that you try to devise has to be data dependent. Right? If all you really got to look at was the training accuracy, how well you fit your data set, there's no hope because you perfectly fit complete nonsense and the real data. So somehow, you know, in the usual pack learning world, we try to have results that are, you know, independent of the data distribution. And the point is, at least for these overparameterized models, that's not going to result in a good theory. And so this is kind of the first thing to have as an intuition. Whatever we think about when we talk about generalization, we need to have some data dependence injected. And what I would say is that as a kind of theory community, we have been very, very slow to develop anything sensible in this direction. And so I think it's a really exciting kind of question that deserves some attention. So I want to present one more empirical paper, but again, I don't want to go too quickly. So if you have questions or comments, tell me. Otherwise, I'll tell you one more kind of interesting piece of information, or a couple more pieces of information, maybe.
First, I have a question, which is,
Yeah.
so like, if you don't do like the complete random labels and random pixels and all that, but say the green line where it's just shuffled pixels,
Yeah.
what would happen then? So
these, what I'm saying is, I haven't reproduced all the experiments from this paper, and it's been reproduced to be extremely robust, basically independent of the data set, independent of the model, independent of the corruption. You know, these neural networks have so many parameters that if you just wait long enough, they will fit all the data you want.
Oh no, I mean in terms of the test accuracy.
Oh, the test accuracy for random labels, that's the one you were asking about?
No. So I see. So the test accuracy. So I understand that the test accuracy for random labels is bad, and that's kind of one of the points. But then you know, so what if you just like you know, modified your data? You know that you had the true data, but you modified it just a little bit. Say by shuffling the pixels, which is the green thing. Like, what would happen then with the test accuracy?
Yeah. So what happens is, it gracefully becomes worse. Mm-hmm. You know, the more brutal your permutation. There's, you know, people do so even in this paper and then in many follow-ups, people inject various levels of noise or, you know, various amounts of corruption. And of course your generalization gets worse and worse because there's kind of less signal, but it's not like a little bit of corruption and you're totally done for. Mm-hmm. You know, it's sort of, and I don't know how to quantify whether it's good or bad, but it's not extremely sharp. It doesn't exponentially go to being bad and then stay there. It kind of, you know, some kind of linear looking thing roughly.
So so does this imply something about like robustness or?
No, that's that's a whole nother talk I could give, but it's really fascinating. So this is also a true statement about neural networks, empirically speaking. If you give me any neural network trained on virtually any task, and you give me any input to the network, I can always perturb it by an imperceptible amount and cause the network to completely fail. So but that perturbation is not random. You know, that I have to search for that perturbation. So if you were to randomly perturb it, you can do pretty well usually. Mm-hmm. And there's a whole world of people who think about what's called adversarial robustness and adversarial learning. And okay, so it's quite fascinating, but I decided not to include that here.
So just to be accurate, so the test accuracy here is the cross-validation accuracy, right?
That's right. So in CFAR 10, I think the standard is there are 50,000 training points and 10,000 held out validation points. That's the way they set it up. And I'm not sure
I'm just saying that the mechanism you create to corrupt the same. I mean, I know that the mechanism you use to, all the testing set is not corrupted.
Oh no, so in this case, the testing set is corrupted in the same way. You apply the same corruption to the whole data set and then you test. Although it wouldn't really matter if you're learning pure noise. You know, you couldn't possibly generalize to anything, but yeah, as a point of fact, I think that's how they set it up.
Okay.
Yeah.
Also a quick question. I'm also an old school studies teacher and trying to wrap my head around deep neural networks. And I'm actually Professor Yajin Wang's student. I know Professor Jianqing Fan. So hi, Professor Fan. Anyway, so quick question. So what you show on this example is basically, I believe, a traditional convolutional neural network. And just by design, the convolution layer will be invariant to the transformations, like some shuffles and random labels. Because if you try like locally connected network or some other that network architecture that has more locality in it, I wonder if this still holds or it just example just because the way convolution layer kind of codifies some of the invariance to the transformation.
So I, there's no theorem exactly about this, but let me put it this way. This experiment is very robust and has nothing to do with the kind of network you're using. It's true for fully connected networks. It's true for convolutional networks. It's true for natural language type networks, transformer-based networks or recurrent networks, depending on your flavor of the day. So I'm trying to present things in an example, but I only present it if I feel like it's true in some empirical sense of the word true. So no small perturbation will kill this effect, as far as I know.
Got it. And did you try like calculating some of the model capacity, like a VC? Because that chart you showed, in terms of the bias variance is just so fascinating, and people are trying to wrap their head around. And,
so I'm going to get to that, but the VC dimension for these things is practically infinite. So VC dimension can't possibly help. And I'm gonna say something about that in a minute.
Okay.
Yeah. Okay, so let me go on to a next paper, which is also very fascinating. Okay, so if you also tell people, oh, the double descent paper, they will basically know which one you mean, and okay, you're going to mean this one. So this is a paper which does the following. Okay, it takes a bunch of different models, and it just draws the kind of plot for the test error. So let me first explain this top left one, but all the phenomena are basically the same. So here on the x-axis, there's the number of parameters in the model. And this particular model is a random feature model over Fourier features. Okay, so that one is like, your model is y of x is the sum on j goes from 1 up to number of parameters, aj e to the I x dot vj. Okay, these are random Fourier features. The vjs are chosen at random, but are frozen. You don't train them. And you just do regression on the ajs. That's your model class. And what they plot here is just the test error, on some sensible data set that they have. And what you see is that, okay, so maybe I should annotate this plot just a bit. Okay, this exactly, again, is the interpolation threshold. And if you look to the left of that orange line, you really get the usual kind of U-shaped curve for the test error. First it goes down, then it goes up. And they call this double descent because the test error descends twice in these examples. Okay, so somehow the philosophy, which I hopefully will have a chance to get to, I prepared a bunch of intuitions I want to give you, that are more mathematical in nature than just going through these examples, is that the interpolation threshold is actually the worst performance. Things are better to the left and things are better to the right. And I will try to sort of explain that in a sense. But the point of this paper is that this phenomenon that the test error first, goes up at the interpolation threshold on one side and then comes back down when you become sufficiently overparameterized, seems to be very robust. Okay, so this is for feature type regression. This is for a neural network trained on a particular task called MNIST. I don't know why it got deleted. So this is very similar to the previous computer vision task. And again, these black lines are the interpolation threshold. Okay, so the training error goes down, 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 down. that's pretty reasonable. And the test error, you know, and this is kind of empirical, but kind of convincing, you know, it goes up and then down, and it depends on the kind of error you use. Here they use a regression error, here they use 0-1 loss. But again, the point is supposed to be that for a very wide range of models, you know, as you make the model more complex on a fixed data set, at first you'll see the usual bias variance picture for the test loss. And then the test loss, rather than being monotonic after a while and just diverging, will actually start decaying again. That often happens, and we do not fully understand why. Okay, there are some theorems about it now, and we have some understanding, which I will try to convey, but this also appears to be a rather robust effect. And so you know, this kind of, again, contradicts the usual statistical learning theory, at least the VC or Rademacher or kind of, you know, very orthodox version of those things. Because, you know, over here, your VC dimension, oops, I should probably draw in another color. So here, the VC dimension, for example, is practically equal to infinity. Okay, not quite, but it's horrible. You know, the kind of bounds you get from using the usual kind of generalization results using VC dimension will tell you the probability of misclassification is bounded above by 17. Okay, and so the theorem, of course, is true, but it's not a very useful result in that regime. And so again, I'm trying to set up the tension of what needs to be explained. Okay, so that's all I wanted to do for empirical papers. Again, you know, if people have a question or something, I'm happy to take it. But I sort of want to get to giving you some actual intuitions rather than just saying crazy things happen and we don't know why. Because, you know, there are good intuitions for some of it now, I would say. Any questions or comments before I plow ahead here? Okay, so let me try to explain what are some basic intuitions for studying this stuff. Oops. This one. Okay, so my plan for the rest of the talk is to present 7 basic intuitions. And, you know, given the amount of discussion we've had so far, which has been great, I almost surely won't get to all of them, but I'll go little by little. Okay, so the first intuition is like an extremely basic linear algebra intuition. So I want to make a dictionary from this setup to something that we study as first year high school students or something like that. Okay, so here we have ND was the number of data points in our setting. And I want to think of each data point as being something like the number of equations in a system of linear equations. Okay, certainly like every data point gives you at most one equation you have to fit because it says the function has to have some value at some point. Now, some data points might actually secretly determine other data points, which is why I put this greater than or equal to thing. Okay, so continuing the dictionary, NP, which is the number of parameters in the model, it becomes the number of variables, right? That's literally our degrees of freedom that we're allowed to move. And therefore, you know, overparameterized systems, overparameterized is what we usually call underdetermined. Okay, and the main point of this intuition is that you expect that there are infinitely many global minima for the training loss. Okay, so I'm not talking about generalization yet, I'm talking about optimization. But, you know, if you have 100 variables and 7 equations, kind of makes sense that there's going to be infinitely many configurations of the variables that are going to allow you to satisfy those equations. Okay, it's a little complicated because the equations aren't exactly linear, but still, it's just meant to be an intuition. Okay, so that's intuition number 1, and I want to build on this intuition to say something about generalization now. So the second intuition is that most, okay, I'll put that in quote, of these minima are bad, okay, i.e. they give bad generalization. But some are very good. Okay, so maybe like the example to keep in mind here is, you know, if you're trying to fit a bunch of points in the plane using polynomials, you know, if I have 10 points and I have polynomials of degree 1,000, there are lots of polynomials that go through those given 10 points. And most of them are kind of highly oscillatory and they do some crazy thing and I can't control them. But it doesn't mean that there aren't some that do exactly what I want. After all, I have a very flexible model class. So somehow when you have an infinite number of minima, the upshot from this is that generalization, any theory of generalization, must be coupled to the optimization procedure. I have to tell you something about which minimum I choose and how I get there. If I tell you nothing other than I drive the training loss to 0, well, you can only do some worst case analysis and life is going to be pretty bad. Okay, so generalization must be coupled to optimization. And again, I put it this way because in the usual, PAC framework, generally, okay, not generally, but often we say, okay, we're just assuming we're at some minimizer over the training set of your loss. We're doing some kind of ERM, and that's it. And we use that, and we're totally agnostic to what the data distribution was. We're totally agnostic to how we found that minimizer, and we say something sensible about generalization. And I'm saying that in this overparameterized world, that probably is not possible. And so you have to say something about how you got there. And that a priori at least makes the problem more exciting or more complicated depending on the way you think about it. Because you can't now separate the question of, oh, how complex was my data from how do I optimize, from how well do I generalize? You somehow have to put them all together. Okay, so I promise I'm working my way towards more sophisticated intuitions. So if you're kind of bored by this because it's all obvious, just give me a minute or two and I promise I will get there. But still, I think these are like basic intuitions that one has to have that I think are important to these problems. Okay, so let me state a third intuition, and then I'll take a break and see if people have something they want to ask or say. So here's one that at first totally blew my mind, but I'll give you a kind of pseudo proof of it, which is 2 lines long. Okay, so the training loss is not convex, or typically not convex. Okay, so that's kind of obvious. No one's going to be surprised at that. You have some very complicated output, model as a function of your trainable parameters. But what I'm going to say is that it's not convex, even near a global minimum, W star of the training loss. So somehow, in my head, I was always brought up to think that if you're optimizing some function, then at least, near the end of your training, you're kind of in some quadratic looking bowl roughly, and you can have some intuition from convex optimization. But I'm here to tell you that that's false. So let me try to draw a picture and convince you of that. So imagine that here is some minimizer W star, and we're in R and P. Okay, so what am I going to do? Well, I'm going to use this previous intuition I had that there are infinitely many global minima. Right? And I'm just going to consider, that connected component of the global minimum set that goes through W star. There could be other connected components, of course. So this is the set of W such that the loss at W is equal to the loss at W star. Okay, that's the orange set. And the basic point is the following, that since the number of parameters is greater than the number of data points I'm trying to fit, we expect, again, this is in quotes, but any sensible model should satisfy this probably. So let me give this thing a name. Let me call this set S. Not very creative, but still. So we expect the dimension of this set to be NP minus ND, which is positive. Okay, but less than NP. You have more than 0 data points, of course. Okay, so unlike in the underparameterized case, where you expect fitting the data to very strongly constrain your parameters and maybe give you some discrete set of choices, you expect to have a continuum of choices here. And now I can prove to you why this set S is not even locally convex. Or sorry, why the loss can't be even locally convex. So let's take a little ball around the point W star, and we can argue like this. So we can say, S is, okay, I can rewrite it a little bit. It's the set of W where the loss at W, so here the training loss everywhere, is less than or equal to the training loss at W star. And the reason I can change the equals to a less than equals is just that this is a global minimum. And so, if I'm equal, I'm also less than equal. And the reason to write it this way is that this set S is a sub-level set of the training loss, therefore. Right? It's the set of points where your training loss is less than or equal to some fixed number. In this case, it's global minimum. So if L train were convex on this ball, right, then so is its sublevel sets. Right, that's the defining property practically of convex functions. A function is convex if and only if all of its sublevel sets are convex. But there's absolutely no reason to believe that this thing is convex. It's just some interesting manifold, right? So for example, I can connect these 2 points and the line segment doesn't lie in the manifold. So unless you have something very special about your model, which causes the set of global minima to actually be affine, or a bunch of things that are affine, you know, there's no reason to believe that even locally near a global minimum, your loss is a convex function. And that sort of is an interesting realization. And it's not as scary as it seems in a sense, because it turns out that we can still talk about optimization using some other criteria. But it's, yeah, I found it to be kind of a fascinating point, not convex. Okay, again, you know, as I advertised, hopefully in the abstract for this talk, I'm not trying to give very rigorous proofs. I just want to give some intuitions for things that I think are important to understand, that we kind of now understand in part as a community. And, you know, for some of these, there are very rigorous theorems that are quite far reaching. And for many of them, there are no theorems. And, you know, I'm just telling you what we believe is true. And so, you know, if you see something wrong with the logic, or you think that something should be refined, I think, you know, it would be very interesting to hear that. So let me pause again after these first 3 intuitions and see if anyone wants to say something. Again, I'm sort of hoping that this will be interactive, but you know, maybe I'm saying things that are, yeah.
Yeah, Jianqing here. No, very interesting. I agree with all 3 points that you said. For point 2, I'm always curious that so far it's always gradient-based algorithm, right? Drive the generalization error down. Even I mean, we have trouble if we give beam proof that we converge to global minimum. We assume that the width is going to infinitely wide. Right? So there are very little theory there, and then there are so many degree of freedom of I mean, tuning the learning rates, and yeah. So and somehow that happens. So it's just very particular, right? So if I give a different, I mean, is always gradient based with some kind of heuristic of choosing the learning rates. Yeah, so I'm very puzzled if I change even the gradient based, if I change a different schedule of, I mean, learning rates, would that still happen?
Yeah, so I think those are great questions. So let me talk about the learning rate, or sorry, the gradient based optimization. So I think I would say 2 things. First of all, you know, part of what I'm trying to say is that, you know, you have to have an optimizer that does something kind of sensible. So when you don't know what to do, being greedy is good. You know, kind of gradient based methods try to get as quickly as possible to an interpolant. They don't wander around, you know, unless they have to. So there's some kind of intuition that by choosing a very simple-minded, very greedy algorithm, you're actually injecting a bunch of regularization in an implicit way into the problem. You know, you're kind of saying you have all these minima, but if your optimization procedure is start at a reasonable starting point and go as quickly as possible to the set of minima, then maybe the minimum you find is also kind of quote unquote reasonable. Okay, that's, you know, very much hand wavy, but there's something important about the point that not any optimizer will work, because of course you can always design an adversarial optimizer that will get you, you know, arbitrarily bad kind of far away minima. No one could stop you. And so we don't fully understand, but all the different variants of gradient descent that people use do a pretty good job of doing optimization in practice for the kind of losses that come up for neural networks. And there, as you say, there are a bunch of theorems. There are some theorems that if your network is wide enough, then with high probability, you know, you'll drive your training loss to 0, that kind of thing. But as you say, that the networks are quite wide. You know, the width grows polynomially in the number of data points. That's the kind of result that's available. But then the other point you bring up is very interesting, and one that I won't get to too much in a sense, but as you say, when you use neural networks in practice, there are an infinite number of choices you have to make. what learning rate to use, what pre-processing, what batch size, are you going to do data augmentation? When are you going to stop training? What loss are you going to, I mean, the list goes on. And the truth is that many of those things are very sensitive, and people often in practice will choose them by something like grid search, believe it or not. They'll just train for a little while, a bajillion different models, and they'll take the one that's doing well. That's not completely uncommon. And so I think that's an important place to develop theory if you want to have kind of very direct practical impact, because these things are clearly analyzable by some theoretical mechanism. And people have been working on that, and I'm interested in that in particular.
I just want to add one point. So grid search was popular, but recently I think there are definitely some advancements, I'm sure you know, in terms of Bayesian hyperparameter optimization with Gaussian process. So I think it's getting less heuristic these days, but I agree with Professor Fan, still very, like brutal way of kind of understanding the parameters and how we pick different hyperparameters.
I mean, I would say that the Bayesian optimization stuff is more heuristic than grid search, because it's not really principled. It's just a massive computation at each step. I mean, it's principled in the sense that it's Bayesian, of course. But my point is that it's a disaster computation. That's like the common theme to a lot of these things people have to do in practice.
Yeah. So by the way, Boris, I like the sentence you use. I always regard gradient methods as a local, rich regression, right? So you are adding an isotropic penalty there, and then you get to, right? So you're really doing local, local regularization all the way, even though the algorithm is gradient methods, but it's really just iteratively rich regression you keep applying.
Right.
Yeah. So you keep regularize. Yeah.
Although they generally don't regularize, or basically.
No, I'm just implicit regularize. No, gradient can be written as minimization of isotropic regularized.
Yeah, that's right. Yeah. So in fact, that point about isotropicity brings me to my next intuition, which I want to cover before time is up. I don't know when I'm supposed to technically stop, but I'm going to keep going until somebody yells at me. So feel free to yell at me. Okay, so here's intuition number 4, and I promise this one's a little bit more substantive than the others. So there's a saving grace that I want to try to explain, and that's that overparameterization, can't spell apparently, actually intuitively implies that you get easy optimization by first order method. So somehow I'm claiming that, yeah, you have to study optimization, but you should intuitively think that it's going to be almost trivial and will converge to a global minimum with high probability, that kind of thing. So let me give you a picture proof of this. Okay, so here's one set of coordinates, here's another set of coordinates. So this is R and P. This is the parameter space in which you normally do the gradient descent. And here you are at some point in this space. And then you have your model F, which in this case is the neural network model. And I want to think of this as a map to R and D. So I take a parameter W and I send it to the vector of values that the network computes on the entire data set. So I goes from 1 up to the number of data points. Okay, so here's like F of the data set comma W if you want. Okay, so that's what I mean by the map F. It's not just, for example, the scalar valued output. I mean, I concatenate the output on every data point I'm trying to train on. So it's some high dimensional vector, right? And over here, the problem is what? That the loss is very complicated, right? That the level sets for the loss, which I'm attempting to draw a cartoon of, are complex. The loss is non-convex. It can have lots of local minima. We don't know what to do. But also what I want to advocate is that these are bad coordinates to work in. Right, so somehow when you have more parameters than data points, your parameters aren't even really identifiable parameters. Okay, you can take that in some like literal sense of identifiability, but you can also just take it intuitively. If you have 17 parameters and 3 equations, then the individual parameters don't mean anything. And so in some sense, it's actually more sensible to work with a system of coordinates, which is just what are the outputs of my network on my data set. That's another system of coordinates you could choose. And one advantage of this system of coordinates, of course, is that the loss is very simple-minded. As a function of the network output, for example, if you had mean squared error loss, the level sets are just very easy. It could just be a convex function. So somehow over here, optimization is easy in the sense that the loss is convex. And over here, optimization is hard in the sense that the loss is non-convex. But of course, you have to pay a price. So let me tell you sort of how to think about it. Okay, so here's what we expect. Here's what overparameterization buys you. You expect that the map F is a submersion. Okay, that's what the geometers would call it. I.e., it just means that the differential of F is surjective. Okay, so dF dF at every W is surjective. So let me draw that in the picture. So, here, the advantage of doing optimization in this parameter space is that all of your parameters are free parameters. That's what the computer actually gets to move. It can say increment this weight by 7, decrease this weight by 0.3. They're not tied variables. On the other hand, the computer doesn't directly compute the values of the output. And so these variables here are correlated. That makes the gradient descent hard. But what surjectivity means is that nonetheless, when you take all the perturbation directions you can at the point W here, and you push them forward to the perturbation directions you can get in the space of outputs, you still get every direction. Okay, so that's what surjectivity buys you. And if you believe that this is true, that for every direction over here, there is a direction that I could have gone in the weight space to kind of go that direction, this is great, because now I can go any direction I want and my loss is convex. Okay, so let me say that in some kind of words. Okay, so if dF is surjective, this implies that always exists what people call a descent direction. Okay, a descent direction means some direction I can go in the parameter space that will strictly decrease my loss, okay, unless I'm at a global minimum. So since here the loss is convex, and I can go any direction I want, nothing is going to stop me. That's sort of the intuition. Okay, so there are no quote unquote bad local minima. So there are no local minima that are not global minima. That's sort of the point of this intuition. Oh, okay. So that's I think that's a really important intuition to have, that in the underparameterized world, you might worry that you're going to get stuck in a local minimum and you don't know how to do optimization by a local search. But the whole point of being overparameterized is that the data points can't really compete with each other. Every data point can have its own parameters. And at least as far as fitting the data goes, you shouldn't be too worried about driving the risk to zero. Now, of course, generalization is a different question, and we have to talk about that. But still, I think this is very important. And I kind of want to, so I have to choose. I don't know when I'm supposed to finish. Did someone who organized the seminar tell me? Because I have a couple more intuitions and I won't get to all of them. So
it's usually 50 minutes, but I think if you go over a bit, that's fine. What do you think, Jinxing?
Oh, well, yeah, I mean, since we interrupt him, yeah, so, and then we actually, yeah, you're right. So, but yeah, since we interrupt him, yeah, I think if Boris, you want to go on, fine, yeah. So Jason is chair, so Jason decide, yeah.
Yeah, I think Boris, maybe, it's probably maybe another like 10 minutes, and then maybe like we'll open it up for maybe 5 minutes of questions, and then people who need to go like maybe a little bit after 12 can leave. But I think technically we're scheduled until 12:30, so. But right. Of course, we do want to accommodate everyone's schedules. So yeah, maybe go until maybe around 12, and then we'll have like a few minutes for questions, and then people who need to leave can leave, and then people who can stay to for further discussions can do that also.
Okay, then you can continue. Yeah, I think it's a great idea. Yeah.
Okay, so let me tell you something which I think is really fascinating. So I want to give a very simple intuition for why the test error should diverge at the interpolation threshold. Why that's the worst point for all these models. If you go back to thinking about that double descent thing, somehow the error was okay, and then right at the interpolation threshold, it exploded. Okay, maybe it's obvious to everyone, but it wasn't obvious to me. I had to think about it. I had to think about it for a while. So that's intuition number 5. So why does the test error blow up at the interpolation threshold? Okay, so let me try to do this on an example. Okay, but a good class of examples. So suppose that your model is y of x, okay, is just a linear regression over a set of nonlinear features phi of x. And as usual, phi of x is some vector of features phi j of x. And here j goes from 1 up to the number of parameters, let's say, oops. So, in this case, the outputs are just scalar. It's not very important. So let me contrast the two cases of over and under parameterized. So in the under parameterized world, when the number of parameters is less than the number of data points, what do we expect? Well, we expect the population covariance to be full rank, right? We expect phi of x transpose to be full rank. So where, when I put the capital X here, I just mean, 1 over number of data points, sum on j goes from 1 up to number of data points, phi of xj transpose. That's just my shorthand for the usual kind of population covariance. Okay, and therefore, when you just solve the normal equations, what do you find? Well, okay, you get W star is something sensible looking. So you do Y time, so Y is a collection of, all the outputs you're supposed to get on your collection of inputs. I'm sort of abbreviating here because I assume everyone knows the form of the normal equations. And, this matrix comes up, and it's good to, when you can invert it, it's relatively easy to write down the optimum for linear regression. So I should have said, L is equal to the MSC loss here. I'm just doing a very simple example, just linear regression on a set of nonlinear features. Okay, so what's the point? The point that I want to bring up is that you're going to have good generalization, right? If and only if you have a good estimate, of all of these matrices versus their kind of actual statistical averages. And the only estimate you should be worried about is this population covariance being close to the true covariance. Okay, so you need to have that your empirical estimate phi of x transpose is approximately equal to the expectation over x of phi of x transpose. The reason is that, if you somehow have a bad estimate for it, because you're inverting this matrix, if you can't do a good job of estimating the small singular values, then it's going to be really painful. You're going to invert it and you're going to have a huge error that you make. So let me say that. Okay, so you're going to have a good estimate of the population covariance by the, of the actual covariance matrix you're supposed to have by the empirical covariance matrix, if and only if the smallest singular value is not too small. That's the hardest thing to estimate, because the size of the smallest singular value has to be bigger than the noise scale that you have by a sampling procedure. Okay, so this is if and only if lambda min of this expectation of phi of x transpose is kind of much bigger than 0. And but you might ask, well, okay, when is the minimum eigenvalue of this kind of population covariance, or I don't know what to call it, the true covariance matrix, strictly positive? Well, that question is answered by the Marchenko-Pastur law. The Marchenko-Pastur tells you much more, of course, but it tells you the size of the smallest singular value. So lambda min looks like this. It looks like 1 minus the square root of number of parameters over number of data points, this quantity squared. Okay, so what you see is that as the number of parameters approaches the number of data points, the smallest eigenvalue of the matrix you're trying to estimate is going to 0. And it's really hard to resolve that smallest eigenvalue. And then when you invert that matrix, it just makes your estimates horrible. So that's supposed to be the explanation of why, when you go from the left somehow, when here's, number of parameters, and here is the interpolation threshold number of data points. So as you approach from here, why the test loss is supposed to blow off. you have just a very poor estimate for the smallest singular value of the matrix you're inverting, and therefore your whole process is just numerically unstable. Okay, so I know I'm being a little bit not careful, but all of this can be made very precise, and you can get actually what is the slope of this blow up. It'll be something that depends on the dimension in which you're working, and some assumptions about the original population covariance matrix, and so on. Okay, so
Boris,
yeah.
If Y is noiseless, does it still blow up? Like there's zero noise in Y.
So this should still blow up. Because
how do you see that? So the eigenvalue argument, it seems like it's pretty clear it blows up if Y has any noise, then it gets multiplied by the eigenvalue and that explodes. But if it's noiseless, is there a way to see?
Yeah, I'm just saying, what you have to do to get the correct answer is replace this by its mean.
Oh, and that's like noise, basically. Okay.
And that is noise. The sampling procedure itself, the ND gives you a noise scale. And if your eigenvalue is just smaller than that noise scale, you have no hope of resolving it. And so this is like a finite sample result. Of course, if it's noiseless and the number of samples goes to infinity, you're okay. But the whole point is for me to approach the number of samples with the number of parameters. I have to keep track of that scale. Yeah. Other questions about this? I want to talk about the other side. There's a trick. It's the same actually, but you have to see the trick somehow. Okay, let me say something about the other side, and then I will stop, and then I will say other things if people want to stick around eventually. So what about the other side? So in the other side, you have to use the fact that you're overparameterized, of course. So let's assume now that we have more parameters than data points. So what's supposed to happen here? Well, so in this case, phi of x transpose is not full rank. And in this setting, when that Hessian of your model is not full rank, you don't optimize in the whole space. You have to project onto the span of that Hessian. So you gradient descent only sees how to say it? Only sees the
interesting seminar
values after applying.
I can barely.
So I need to project. So I'll write it proj the orthogonal projection onto the span of that Hessian. So I have to do the span of phi of x transpose if I'm sort of being more or less careful. So this is like the column space of phi. And when you write out the formula for this thing, this has this formula. This is phi of x. And then crucially, you have the other matrix. You have the transpose in the other place. Okay, so in the overparameterized world, this one is now invertible. And the key point is that the transpose is on the left and not on the right. So somehow, when you're overparameterized, you have to first project onto the directions where your Hessian's non-degenerate and then do something. But now the same exact argument holds, right? So now this matrix is invertible, but again, you have to have a good estimate of its smallest singular value of this matrix, or smallest eigenvalue. And again, it's going to blow up by the Marchenko-Pasteur law, except the role of NP and ND are just reversed. Okay, so just as before, Marchenko-Pasteur says that lambda min of the thing you're trying to approximate, which would give you the correct answer if you plugged it in, is like square root, actually it's the other way, 1 minus square root. But now you're supposed to do number of data points over number of parameters squared. So again, you have sensitivity issues on the smallest eigenvalue. You can't invert your matrix with high confidence, and things go very poorly. Okay, so let me stop. I've hit 12 o'clock exactly. Promised I wouldn't go more than 10 minutes after the previous discussion. So I'm happy to have some kind of discussion, have questions and all that. And if people want, I also prepared one more intuition, well, two more intuitions really, but one more main one that I could present about how to see this in the case of linear regression. there's some kind of nice geometrical argument for seeing the optimizer and the initialization and the generalization somehow all tied together. That's the only example I can do in one slide.
Yeah, so I guess we should officially conclude, but thanks a lot, Boris. It was very illuminating and insightful and very just fascinating, and you did a great job. So
thank you.
Thanks a lot for everything.